You might be thinking, wow, look at that awesome sketchy burner. I wonder how someone would make a burner like that. Well, today we're going to show you how someone would make a burner like that. For this project, we'll be using both 3D printed parts and 3D printer parts. We're going to find out how well 3D printed parts can hold up to the heat generated by welding, and we'll also learn a hard lesson about designing burners for cooking. So we originally printed this fixture piece from ABS plastic, but there was problems. There was a lot of warping and shrinkage, and so we ended up reprinting it out of a material that is a lot more expensive, but it was also a lot more dimensionally stable. You can see the original piece here on the left. This ABS part came in almost 60 thousandths small on this dimension, but the PET carbon fiber part was within 6 thousandths, which is definitely a tolerance that we can live with. This part of the fixture was fine dimensionally, but the way it was designed would have made the fit up and welding pretty difficult. So we redesigned it and replaced it with this blue fixture, which also happens to show up a lot better on the camera. These two tubes will be mounted just above the propane orifices. They'll allow propane gas to mix with air before the flame starts about halfway up the tube. Other than a few burns from weld spatter, this fixture held up to the welding just fine. We used it to make 4 repeat weldments back to back. If you've watched any of our other videos, you may be noticing a common thread. We struggle to get through a project without using a 3D printer or laser cutter at least once. Now that we have all the pieces we need, we're going to do a quick dry fit to make sure that everything fits together properly. We had to get a little creative coming up with a way to hold this plate up. If we were to design the burner again, we'd flip this mounting tab over so the plate could rest on top of it using gravity. This acrylic piece will come in handy when we start welding because we can see through it and it's not going to block our view. Everything worked out really well in the dry fit test, so now it's time to fixture these parts and start welding. Everything is now tacked up. We did try a few full welds down here just to see how the fixture would handle the heat, but as you can see, it didn't handle it very well. The steel got too hot and melted the fixture just a little bit. So we switched to just doing tack welds while the parts are in the fixture, and then we'll pull the fixture and do the rest of the welding without it. The frame of the burner is now complete, so we'll move on to the propane manifold piece. This piece will eventually be made from aluminum, but for now we 3D printed it from PET carbon fiber. That way we can ensure that it fits and functions correctly before we get it machined. These brass nozzles are actually 3D printer replacement parts. Normally one is mounted to a 3D printer and molten plastic is pushed through it to build a part layer by layer. For our project, they'll be used for propane orifices. Since they're threaded, they can easily be removed for cleaning or replacement. This propane hose with the regulator is just an off-the-shelf retail product. Alright guys, we're going to get this hooked up and lit for the first time. We'll see how it works. Alright, we're not sure how the plastic is going to hold up to the heat, so we decided to take it outside, get the tank as far away as we can. We brought our fire extinguisher and we're going to try to see how long it goes, see how long the plastic holds up. We're checking the temperature down here to see how much heat may have transferred to our 3D printed manifold. Alright, this has cooled down a little, so we're going to take out the screws and remove this plastic printed part. We're going to see if there's any damage caused by the heat. There is no damage around these nozzles, so the prototype has done its job well. Now we can confidently move forward getting its replacement part machined from aluminum. Okay, now we want to see how our burner compares to other commercially available propane burners. We'll start by setting a benchmark with my portable stove. The manufacturer advertises a heat output of 12,000 BTUs. We want to keep our boil time tests as scientific as possible, so we're going to follow the exact same process every time. We're going to take 2 gallons of cold water from our sink, carefully measured, then we're going to pour it into this stainless steel pot. Then we'll take our thermometer and probe the water to make sure the temperature is about the same to start with on every test. Now we'll test this commercially made burner that we have here in our shop. And finally, we'll test the burner that we built. Alright, so after doing the boil test with this burner, we saw a design issue. So the flames are coming up through right here. They hit the bottom of the pot and they're spreading out in every direction. And what we think is happening is the flames are coming up through this circle. They want to spread out, but this is preventing them from going where they need to go. It's captivating the flames. So we're going to remove this ring. We think it's a flaw and it'll work better without. So we're going to cut it out and then we'll retest it. We think we'll get faster results if we can deliver a little more propane, so we're going to use a precision drill bit to modify a couple of nozzles to have a 1.1 millimeter hole instead of the original 1 millimeter hole. Okay, we've compiled all of our test data and created a chart to display the results. The huge outlier on the bottom shows the results from the test with my portable camp stove. It wasn't even in the same ballpark as the high output burners. Here's the same chart again, but we've removed the portable stove outlier. Our original burner and the high output retail stove performed almost exactly the same at 7.75 minutes. Cutting out the steel ring shaved off 30 seconds, bringing the boil time down to 7.25 minutes. Swapping out the 1mm nozzles for 1.1mm nozzles shaved another 45 seconds, bringing the boil time down to 6.5 minutes. We also performed one more test where we increased the nozzle size to 1.2mm, but we didn't get any improvement in the boil time on that test. Our modifications brought big improvements, but there are still changes to be made. The pot we used wasn't really the ideal tool for testing the potential of these stoves. We used stainless steel, but aluminum would heat up much quicker and deliver faster boil times. Our pot was about 12.5 inches in diameter, but our burner is designed to handle pots up to 18 inches in diameter. Increasing the pot diameter from 12.5 to 18 inches would double the surface area on the bottom of the pot. While doing the last two boil tests, I had to put on a jacket and gloves before probing the water temperature because the flames were pushing out far beyond the bottom of the pot and they were burning my arm. A larger pot would be able to transfer a lot of the heat to the water rather than transferring it to the surrounding air and my arm. We hope you've enjoyed watching us play with flames, and we hope to see you next time.